Today, we're going to dive into a technology that was literally born out of a need for perfection. We're talking about building software that, for all intents and purposes, simply cannot be allowed to fail.
I mean, think about it for a second. The systems that run our world, telecom networks, banking systems, massive messaging apps, downtime for them isn't just an oopsie. It's a major problem. So the question is, how do you even begin to build for that kind of reliability, especially when you're dealing with millions of users all at once?
Well, this exact problem landed on the desk of Ericsson back in the 1980s. Their telephone switches were the backbone of everything, and they had to be available 9/9 of the time. That's just over 30 milliseconds of downtime a year. Their solution was pretty radical. They didn't just tweak what they had, they built an entirely new programming language from the ground up to solve this, and they called it Erlang.
Okay, so let's peel back the layers and see what makes Erlang tick. It all starts with its most fundamental concept, the process.
Now, first things first, you have to forget everything you think you know about an operating system process. An Erlang process is a completely different animal. It runs inside Erlang's own virtual machine called the Beam, and it is incredibly lightweight, uses a tiny amount of memory, and is completely isolated from everything else. Think of it like a tiny, self-sufficient worker in a giant factory.
And the scale here, well, it's just mind-bending. Because these processes are so cheap to create and run, a single server can handle millions of them at the same time. Not thousands, millions. This is the absolute foundation for how Erlang deals with huge concurrent workloads. And here you can really see the difference. An Erlang process spins up in microseconds, but the real game changer is that last row, isolation. Each Erlang process has its own little bubble of memory. So if one of them fails, it just vanishes. It doesn't affect any of its neighbors. An OS thread, on the other hand, shares memory. If one of those goes down, it can take the whole application with it. It's a huge difference.
So we have millions of these little isolated workers running around. That's great, right? But if they're all isolated, how do they actually work together? How do they communicate?
The answer is simple and honestly pretty elegant. They don't share anything. Instead, they send messages to each other. It's a lot like sending postal mail. Every single process has its own little mailbox. Other processes can drop messages in that mailbox, and the process can check its mail whenever it's ready. This whole idea is known as the actor model, and it's key to Erlang's stability. Right? And this share-nothing design is the secret sauce. Because processes can't just reach in and mess with each other's data, you totally eliminate a whole class of really nasty bugs. Things like race conditions and deadlocks that programmers in other languages spend ages trying to fix. It's just a fundamentally safer way to build things. Now, these lightweight processes and this messaging system are the building blocks. They're super important. But the real architectural magic comes from a set of libraries and design principles called the Open Telecom Platform, or OTP for short. This is where things get really interesting.
At the very heart of OTP is a philosophy that sounds completely wrong when you first hear it. That philosophy is let it crash. Yeah, you heard that right. Instead of writing tons of code to try and predict and handle every single possible error, the Erlang way is to just accept that things will fail and to build the system around that reality.
So how is that not just total chaos?
It works because of a simple but brilliant structure. You have your worker processes, which, do the actual work, and then you have special supervisor processes. And their only job, their entire reason for existing, is to watch over the workers. And these workers and supervisors are organized into what's called a supervision tree. You can have supervisors watching other supervisors who are watching the workers way down at the bottom. This creates this incredibly resilient structure where a failure in one tiny little part of the system gets contained and handled by its direct boss without ever causing a problem for the rest of the application. And here is that beautiful self-healing loop in action. A worker hits an error and just crashes. But because it's isolated, nothing else cares. Its supervisor immediately gets notified, and depending on the rules you gave it, it just restarts the worker in a fresh, clean state. The whole thing happens automatically, in microseconds. This supervision model is already super powerful, right? But OTP gives us even more. To make it even easier to build these kinds of systems, it gives us standardized, battle-tested templates called OTP behaviors. You can think of behaviors as basically blueprints for common jobs. Like if you need a process that acts like a server, you just use the gen server behavior. It gives you all the generic code for free. All you have to do is plug in your specific logic. It takes care of all the tricky generic stuff for you.
And the benefit here is massive. It's not just about building things faster. It also means the code is way more maintainable. When every developer in the community is using the same standard patterns, it becomes so much easier to jump into a new project and understand what's going on. It's like everyone is speaking the same architectural language.
Okay, let's bring this all home. We've got lightweight, isolated processes, we have a clean way for them to talk to each other, and we have this amazing supervision framework that handles failures automatically. So what does all that add up to? It all boils down to this really profound formula for reliability. The total isolation of processes means errors can't spread, and the supervision framework acts like an automated immune system, instantly fixing problems as they pop up. What you get is a system that can literally heal itself without a human ever having to intervene.
And that brings us right back to the beginning. This architecture, with its millions of tiny, supervised, self-healing processes, is the blueprint for how we build the hyper-reliable, massively concurrent systems that our modern world absolutely depends on. From telecom switches to routers to messaging platforms, the principles that Erlang and OTP pioneered are the unsung heroes keeping us all connected.